Question 34. What mass of nitrogen gas at STP has a volume of 1 liter? Now, STP is an acronym, okay, which stands for Standard Temperature and Pressure. Okay, standard temperature and pressure. Okay, standard temperature and pressure is always 1 atmosphere and 0 degrees Celsius, or 273 Kelvin. Okay. Anytime you're told that you are at STP, that means that you already know 2 pieces of information, the temperature and the pressure. Okay? So at standard temperature and pressure, we already know the temperature and the pressure. So let's take a look at our ideal gas law and plug that information in. Right, so we would have pressure, 1 atmosphere. Temperature, 273 K. Okay, right away, we know those things just by saying STP. We're told a volume of 1 liter, and we always know R. And I'm not going to write the units because it's exhausting. I will when I write the rest of the question, though. And we're asked for moles. Okay, so PV equals nRT. So N equals PV over RT. So we'll have 1 atmosphere times 1 liter over R times the temperature and we'll find that that is 4.464 times 10 to the minus 2 moles of N2. Okay, but the question says what mass of nitrogen gas? So now that I know moles of nitrogen gas, we already know how to convert from moles to grams. So let's go ahead and do that. Right, and let's remember we're tracking at the 3rd sig figs because we have 3 sig figs up there. I want to keep more digits because I don't want to round early. Okay, if I round early, I risk the mistake, the possibility of making rounding errors. Okay, and nitrogen, dinitrogen is 28 grams of nitrogen per mole of nitrogen. Remember, there's 2 atoms there. Each one weighs 14. And then we end up with an answer of 1.25 grams of nitrogen gas. Which of these is predicted by the gas laws? So increasing the volume increases the pressure. Right? Remember we said that pressure and volume are inversely proportional. So that can't be true. Cooling a gas increases its pressure. Right? So remember, pressure and temperature are directly proportional. So if I decrease the temperature, I should also decrease the pressure. So that's not true. By adding more gas particles at constant temperature decreases its volume. Okay? Think about that in terms of blowing up a balloon. Right? If you're blowing up a balloon, you're adding more gas to the inside of the balloon and the balloon gets bigger, right? So we're increasing the volume. So that one can't be true. Cooling a gas will cause the volume to decrease. So volume and temperature are directly proportional. So as I decrease the temperature, I should also decrease the volume. So that one is true. meaning that that one cannot be. Okay, this is a marvelously complex problem. Okay, so we're going to take a few minutes to go through it. So density is mass divided by volume. Okay, and in this problem, we already know what the grams are. Right? We're told that right here. Right? So what we need to find is the liters. Okay? So with the ideal gas law, we're already told the temperature, 15 degrees C. We're told the pressure, 745 millimeters of mercury. R is a constant, so we already have that. So what I want is volume. Okay? So what I'm missing here in my information is the moles. Okay? Now, if I know the mass of a compound and I know the formula for the compound, I can find the moles of the compound. Okay? That's a skill that we learned right off the bat in doing chemical calculations. Right? So 1 gram of CH4, and the mass of CH4 is 16.05 grams per mole. And we find that we have 6.231 times 10 to the minus 2 moles of CH4. We're tracking that at the third sig fig. Okay? So now I just need to make sure that everything is in the right units. So right now I have millimeters of mercury, so let's convert that to atmospheres. And that comes out to be 0.980 ATM. And temperature is 288 Kelvin. All right, so let's rearrange to solve for the volume. So looking at the ideal gas law, if I get volume by itself on the left-hand side, volume equals nRT over P. So now I have the moles, I have the pressure, I have the temperature, and I know the R constant already, so I can solve for the volume. And that's the missing piece. So I get 6.231 third sig fig times 10 to the minus 2 moles times 0.08206 liters atmospheres over moles Kelvin times 288 Kelvin all over 0.980 ATM. And we'll find out that the volume equals 1.5 liters. So the density equals 1 gram divided by 1.5 liters ends up being 0.667 grams per liter. Nice and involved problem. We got all kinds of writing on that slide. Okay. A 2.5 liter flask at 25 degrees C contains 5 grams of each oxygen and nitrogen gas. Okay. What is the total pressure of gas within the vessel? So in order to solve this, I need total moles. Okay, So total moles will tell us total pressure. Okay. So let me rewrite this in such a way that it makes a little bit of sense. So I can write my ideal gas law as pressure total times volume is related to moles total times RT. Okay, so in order to find pressure total, I need moles total. Okay, so I've got 5 grams of each oxygen and nitrogen gases. So we know how to convert grams to moles. And we do the nitrogen gas. And we get 0.1786 moles of N2. Okay, so total those up, I've got 0.335 moles total. Okay, so I'm going to erase this real quick so that I can complete my ideal gas law equation. Okay, so hopefully you've written this much down, and we'll come back. Now that we have that information, we can utilize it. And I want to solve for P, so P equals nRT over V. So pressure equals 0.335 moles times the R value, 0.8206 liters atmospheres over moles Kelvin, times 298 K, all over 2.5 liters. And we'll find that the total pressure equals 3.28 atmospheres. Okay, so before we do anything more, we need to learn about a new law, and it's a thing called Dalton's law of partial pressures. And what Dalton's law of partial pressures says is that the sum, so with a mixture of gases, total pressure of the mixture equals the sum of the individual pressures. Okay, so I can calculate the pressure of each individual gas, and then the sum of those pressures equals the total pressure of the mixture. Okay, and the way this sort of looks in a much more less wordy fashion is that pressure total will be equal to the pressure of gas A plus the pressure of gas B plus the pressure of gas C, and for however many gases I have. Okay? So looking at this particular problem, so a flask contains liquid water and hydrogen gas at 22 degrees Celsius. The vapor pressure, that means the pressure of the water gas, okay, H2O gas in this flask, that is the vapor pressure of water, okay, at 22 degrees is 19.8 millimeters of mercury. If the total pressure is 765, what is the pressure of just the hydrogen gas? Okay, so pressure total equals the pressure of both gases. Pressure of the water gas, or the vapor pressure, plus the pressure of the H2 gas, right? So pressure total minus pressure of H2O equals the pressure of H2. So it's a simple subtraction problem. I say 765.0 millimeters of mercury minus 19.8 millimeters of mercury equals 745.2 millimeters of mercury for the H2 gas.